Chapter 6. The Tournament Engine. Tournament Manager. Sol. The Tournament Manager. Sol contract is the central orchestrator of the tournament. It is responsible for managing the tournament's state, player registrations, and the generation and progression of the match bracket. Contract design and security. The contract will be built using modern Solidity practices and will inherit from Xrpl's battle-tested libraries to ensure a high level of security from the outset. Ownable. This contract will be used to establish a clear administrative role. The owner, likely a multi-sig wallet controlled by the development team, will have exclusive privileges to perform critical functions, such as creating new tournaments or pausing the system in an emergency. Pausable. Inheriting from this contract provides an essential emergency stop mechanism. 46. If a vulnerability is discovered or an attack is underway, the owner can call the pause function to halt all state-changing operations, like new registrations or match reporting, giving the team time to address the issue. Re-entrancy guard. This modifier will be applied to functions that involve external calls or token transfers to prevent re-entrancy attacks, a common and dangerous vulnerability in smart contracts. 48. On-chain data structures. Efficient and gas-conscious data structures are essential for on-chain performance. The contract will utilize a combination of mappings and dynamic arrays to store tournament data. 49. Player information. A mapping will be used to store data for each registered player, keyed by their wallet address. Mapping address GT player info public players. The player info struct will contain relevant data such as a unique ID, their current status, and potentially their chosen character NFT ID. Bracket management. The tournament bracket will be represented by a dynamic array of match structs. Match public matches. The match struct will define the participants of a match, the winner, and its current state, EGD pending complete. Struct match, UN2256 ID, address player 1, address player 2, address winner, match state, bracket generation logic. For a single elimination tournament, the bracket generation logic must be deterministic and executed on-chain. Upon the close of the registration period, an owner-restricted function generate bracket will be called. For an 8-player tournament, this function will take the list of registered player addresses. Optionally, seed the players based on a ranking system or randomize their initial positions. Create the initial 4 first-round matches and populate the matches array. Subsequently, create the placeholder structs for the 2 semifinal matches and the final match, leaving the player slots empty. These will be filled in as the winners of the preceding rounds are determined. While JavaScript libraries for bracket management exist, their logic must be carefully ported to Solidity, with a strong focus on minimizing gas consumption during the creation and update processes. 51. State machine implementation. To enforce a logical flow of operations, the contract will be designed as a finite state machine. An enum will define the possible states of the tournament. Enum tournament. State, registration. Open, in progress, finished, cancelled. A state variable tournament. State public current state will track the tournament's phase. Functions will be protected by modifiers that check the current state, ensuring, for example, that players can only register when current state is registration open, and match results can only be reported when it is in progress. This prevents out-of-order operations and enhances the contract's predictability and security. Chapter 7. The Prize Vault and AMP. Payout Automation. MatchEscrow.sol. The MatchEscrow.sol contract acts as the secure, automated prize vault. Its sole purpose is to hold player entry fees during the tournament and distribute them to the winners upon completion, without requiring manual intervention. Escrow and payout logic. This contract will be designed for simplicity and security. It will hold the wrapped versions of the MB589 MG589 tokens that have been bridged over from the Xrpl via the Facets protocol. Deposit entry fee. When a player registers via the tournament manager, the manager contract will call a function on the MatchEscrow contract to pull the required entry fee from the player's wallet. This requires the player to have first approved the MatchEscrow contract to spend their wrapped tokens. The function will verify that the call is coming from the authorized tournament manager contract. Distribute prizes. This is the most critical function and will be heavily restricted. It can only be called by the tournament manager contract, and only when the tournament state is finished. Upon being called, it will receive the addresses of the winners and the amounts to be paid. It will then execute the transfer calls to send the wrap tokens from its own balance to the winners' addresses. This automated programmatic payout is a core benefit of using smart contracts, as it removes the need for a trusted human administrator to handle the prize pool. Trustless outcome reporting. The link between the off-chain game and the on-chain contract is the reporting of match outcomes. The authoritative game server is the source of this information. Server signature. After a match is completed, the authoritative game server will determine the winner. It will then construct a message containing the unique match ID and the winner address. This message is then cryptographically signed using a private key known only to the server. On-chain submission. The server, or a designated relayer, calls the report match winner, match ID, winner address, server signature, function on the tournament manager contract. Signature verification. The tournament manager contract holds the public key corresponding to the server's private key. It uses an Xrpl operation to verify that the provided signature is valid and was generated by the authorized server for that specific message. If the signature is valid, the contract updates the state of the match, records the winner, and advances the winner to the next round in the bracket. This mechanism ensures that only the trusted game server can update the on-chain state of the tournament, preventing unauthorized or fraudulent match reports. Chapter 8. Dispute Resolution and AMP. Fair play. While the server signature model provides a degree of security, it still relies on trusting that the server itself is not malicious or compromised. A truly decentralized system must account for this trust assumption and provide a mechanism for players to challenge incorrect outcomes. The choice of a dispute resolution model involves a significant trade-off between decentralization, operational complexity, and user experience. Option A, MVP, Centralized Admin Multisig. For the initial launch, a pragmatic and straightforward approach is to implement a centralized dispute resolution process managed by a multisig wallet. Mechanism. If a player believes a match outcome was reported incorrectly, they can submit a dispute ticket to the game administrators through an off-chain channel, e.g. a Discord server or support website. They would need to provide evidence, such as a video recording of the match. Adjudication. A committee of trusted individuals, the multi-sig owners, would review the evidence. If they agree that the server's report was incorrect, they can use their multi-sig wallet to call a privileged function on the tournament manager contract, such as override match winner, match ID, correct winner address, to manually correct the on-chain state. Pros and AMP, cons. This model is simple to implement and provides a fast resolution path for players. However, it is fully centralized and relies on the integrity of the admin committee, which runs counter to the trustless ethos of blockchain. Option B, advanced, optimistic challenge window. A more decentralized and trust-minimized approach can be adapted from the principles of optimistic rollups. This creates an on-chain court where server claims can be challenged and verified. Process, pre-match commitment. Before a match begins, the authoritative server calculates a hash of the deterministic game replay log, a complete record of all player inputs, and submits this hash to the tournament manager contract. This acts as a commitment to a single version of events. Outcome assertion. After the match, the server reports the winner as usual. This action starts a challenge period, e.g. 1 hour. The prize payout is frozen during this window. Challenge. The losing player can challenge the outcome by calling a challenge, match ID function, and staking a bond, e.g. a certain amount of MB589 tokens. This signals a dispute. On-chain verification, fraud proof. The challenge forces the server to reveal its evidence. The server must submit the full replay log to a verifier contract, or post it to IPFS and submit the link. This verifier contract is a specialized, gas-optimized smart contract that can re-simulate the game's logic based on the replay log. Because the original hash of the log was committed on-chain, the server cannot submit a fraudulent log. The verifier contract reruns the simulation and determines the true winner. Slashing and resolution. If the verifier finds that the server's initial report was incorrect, the server's own staked bond is slashed and awarded to the challenger as a reward. The match outcome is corrected on-chain. If the server's report was correct, the challenger loses their bond, which is awarded to the server to compensate for the cost of the dispute. This optimistic model creates a powerful economic incentive for the server to always report honestly, as dishonesty can be proven and penalized on-chain. It moves the system closer to a truly trustless state. However, this comes at the cost of increased complexity and a delay in prize payouts due to the challenge window. A phased implementation is the most prudent path forward. The game should launch with a simpler admin multisig model to prioritize a smooth and fast user experience. The development of the more complex optimistic challenge system can proceed in parallel, to be introduced in a later version as a feature for high-stakes professional tournaments, allowing the ecosystem to mature into its decentralized ideal without sacrificing initial playability and user satisfaction. Table 2. Smart Contract Module Breakdown. Contract Name. Primary Responsibility. Key State Variables. Key Functions, Emitted Events. Dependencies. Tournament. Manager. Sol manages tournament lifecycle, player registration, and bracket state. Mapping address and GT, player info players, matches, tournament state current state, address server, public key, register player in generate bracket, report match winner, advance winner, player, registered bracket, generated match, completed tournament, finished match escrow, Sol, dispute resolution, Sol, ownable, Sol, pausable, Sol match escrow, Sol securely holds and automatically distributes player entry fees. IERC20 wrapped prize token, address tournament manager, UN256 total prize pool, deposit entry fee, distribute prizes, fee deposited prize distributed IERC20.SOL, reentrancy guard, Sol dispute resolution.SOL in advanced, manages the optimistic challenge game for match outcomes. Mapping UN256 and JEET, challenge, challenges, UN256 challenge, period, UN256 challenge, bond, challenge match, submit replay proof, resolve challenge, match, challenge resolved, tournament, monitor.sol, replay verifier.sol. Part 4, the bridge, connecting Xrpl value to Songbird logic. The successful integration of the Xrpl asset layer and the Songbird logic layer hinges on the security and efficiency of the cross-chain bridge. This component is responsible for facilitating the flow of value between the two ecosystems, specifically for handling tournament entry fees and prize payouts. The choice of bridging technology is one of the most critical security decisions in the project's architecture. Chapter 9. Bridging Architectures Compared. There are several models for cross-chain communication, each with distinct trade-offs between security, decentralization, and implementation complexity. Centralized custodial bridges. This is the simplest model. A trusted centralized entity, the custodian, operates wallets on both chains. To bridge assets from Xrpl to Songbird, a user sends their MB589 tokens to the custodian's Xrpl address. The custodian then mints an equivalent amount of a wrapped or IOU token on Songbird and sends it to the user's EVM address. The process is reversed for withdrawals. While easy to use and build, this model introduces a massive single point of failure and significant counterparty risk. If the custodian is hacked, misbehaves, or is shut down, all bridged assets can be lost. Trust Minimized Bridges Facets Protocol. This model seeks to remove the single trusted custodian and replace it with a decentralized system of economic incentives and cryptographic proofs. Flare's Facets Protocol is a prime example of this approach. Instead of a single custodian, it uses a network of independent agents who are economically incentivized to act honestly. Assets are not held in a single pot, but are managed by these agents, who must lock up significant collateral to participate. The system uses on-chain oracles, like the Flare data connector, to cryptographically verify events on the source chain Xrpl, before allowing actions, like minting, on the destination chain, Songbird. This design is far more secure and decentralized, but is also more complex to implement and may involve higher latency. For a project handling a significant prize pool, the security risks associated with a centralized bridge are unacceptable. Therefore, the Facets protocol is the recommended solution, as its trust-minimized design aligns with the core principles of decentralization and provides superior protection for player funds. Chapter 10. Implementing the Facets protocol. The Facets protocol will be the backbone of the game's cross-chain economy. The project's back-end systems will need to interact with this protocol to manage the flow of entry fees into the Songbird escrow and the payout of prizes back to the Xrpl. The flow, minting wrapped tokens for tournament escrow. This process moves value from the Xrpl to Songbird, so it can be managed by the Match Escrow smart contract. User action and AMP. Fee calculation. A player decides to enter a tournament through the game client. The client communicates this to the backend, which calculates the required entry fee in MB589 tokens. Interaction with an F-Assets agent. The game's backend, acting on the player's behalf, after receiving the player's MB589 tokens into a temporary project-controlled hot wallet, initiates a minting process with a registered F-Assets agent. It sends the required amount of real MB589 tokens to the agent's designated Xrpl address. Flare Data Connector, FDC. Verification. The FDC, one of Flare's enshrined protocols, is a decentralized Oracle network that monitors the state of external chains. The FDC observes the Xrpl, confirms that the backend's payment to the agent has been finalized, and submits a cryptographic proof of this transaction to the F-Assets smart contracts on the Songbird network. Minting on Songbird. Upon receiving the valid proof from the FDC, the F-Assets contract on Songbird automatically mints an equivalent amount of a wrapped ERC20 compliant version of the token, e.g. SMB-V9. This newly minted SMB-589 is then transferred directly to the MatchEscrow.SOL smart contract, officially securing the player's spot in the tournament. The flow, redeeming wrapped tokens for prize payout. This process moves value from Songbird back to the Xrpl to deliver the grand prize to the winner. Payout trigger from escrow. After the tournament concludes, the tournament manager triggers the distribute prizes function in the Match Escrow contract. The escrow contract then transfers the accumulated pool of wrapped SMB589 tokens to the winner's Songbird wallet address. Redemption request. The game's backend, now acting on the winner's behalf, initiates a redemption transaction with an F-Assets agent. This involves calling a function on the F-Assets contract on Songbird, which burns the winner's SMB589 tokens. Agent payout on Xrpl. The Facets agent, who is monitoring the Songbird network, observes this burn event. The event serves as a verifiable instruction for the agent to release the underlying assets. The agent then executes a payment transaction on the Xrpl, sending the equivalent amount of real MB589 tokens from their reserves to the winner's designated Xrpl address. The player receives their prize in its native form, ready to be held or traded on the Xrpl DEX. Agent collateralization and operational considerations. To ensure the system is always solvent, every wrapped token is backed by a real token, Facets agents are required to lock up a significant amount of collateral, typically a mix of stablecoins and the network's native token, SGB on Songbird. The system requires agents to be over-collateralized, meaning the value of their locked collateral is substantially higher than the value of the assets they are bridging, e.g. a 140% collateral ratio. If an agent misbehaves or fails to process a redemption, their collateral can be liquidated to make the user whole. For this project, the development team will need to either partner with an established professional F-Assets agent or run its own agent infrastructure. Running a dedicated agent provides more control over the user experience and fee structure, but also requires significant capital for collateral and the operational overhead of maintaining the necessary nodes and software. Table 3. Cross-chain bridge, options analysis, features centralized custodian, Oracle-based relayer F-Assets protocol, security model, trusted, Oracle network, Trust minimized, crypto-economic decentralization level, centralized, single entity, semi-decentralized, decentralized, agent network, implementation complexity, low-medium, high transact ion speed fast, medium, Oracle latency, medium, FDC verification latency, key risk factor custodian hacked or rugged, Oracle compromised or corrupted, agent collusion or smart contract bug. Part 5. The gameplay layer, real-time action in AMP, off-chain systems. While the blockchain components provide the economic and governance backbone, the core player experience of a fast-paced fighting game is forged in the real-time, off-chain gameplay layer. This layer must be engineered for low latency, responsiveness, and most importantly, cheat prevention. Chapter 11. The authoritative server architecture. For any competitive player-versus-player PvP game, an authoritative server architecture is non-negotiable. The alternative, a peer-to-peer P2P model where clients communicate directly, is highly susceptible to cheating, as any player could modify their game client to give themselves an unfair advantage, e.g., increased speed, invincibility, higher damage. 20. The dumb client smart server model. The foundational principle is that the player's client is treated as an untrusted input device. Its only role is to capture the player's actions, e.g., move left, press heavy punch, and send them to the server as quickly as possible. The server, in contrast, is the smart component. It maintains the definitive state of the game world for each match. It receives input streams from both players, processes them in a fixed, deterministic order, and runs the game simulation. The server calculates all movement, physics, collision detection, and damage. It then broadcasts the updated authoritative game state back to both clients, whose only job is to render that state on screen. This model makes it impossible for a player to cheat by manipulating their local game files, as the server's simulation would simply override any invalid state they attempt to create. Netcode for fighting games. To provide a smooth and responsive feel, especially over imperfect internet connections, the server will implement a sophisticated networking model known as deterministic rollback netcode. Unlike simple delay-based netcode, which can feel sluggish, rollback netcode works as follows. Prediction. The game client doesn't wait for the server to confirm every action. It immediately executes the local player's input and predicts the opponent's actions based on their last known state. Correction. When an input from the opponent arrives from the server, the client rolls back the game state to the last confirmed state, applies both the local and remote inputs in the correct order, and resimulates the game forward to the current frame. Result. This entire process happens in milliseconds, creating the illusion of a lag-free experience. The server remains the authoritative source, but the client-side prediction and rollback make the gameplay feel instantaneous. Match adjudication and on-chain reporting. The server's final and most critical responsibility in the context of this hybrid architecture is to act as the trusted adjudicator for match outcomes. Final state. When the game simulation reaches a terminal state, e.g., one player's health reaches 0, the server declares a winner. Signed outcome. The server then creates a data packet containing the unique match ID and the winner address. It signs this packet with its private key, creating a verifiable attestation of the result. Submission to Songbird. This signed message is then submitted to the report match winner function on the tournament manager smart contract on the Songbird network, triggering the on-chain state update. Replay hashes for dispute resolution. To support the advanced optimistic dispute resolution model, the server must perform one additional step. Before a match begins, it must initialize a deterministic replay log that will record every single player input with a corresponding timestamp or frame number. Pre-match commitment. The server calculates the KEKAK 256 hash of this initially empty log seed or a unique match identifier. This hash is committed to the tournament manager contract on-chain before gameplay starts. Immutable evidence. As the match progresses, the server appends every input from both players to the log. At the end of the match, the final log represents a complete, deterministic record of the entire game. If a dispute is raised, this log can be submitted as evidence. Because its initial state was hashed and stored on-chain, it is tamper-proof. Any alteration to the log would result in a different hash, revealing the fraud. 61. Chapter 12. The Graphics Pipeline for 2.5D Meme Warriors. The visual identity of the game is defined by its 2.5D style and its meme warrior theme. This combination suggests a vibrant, stylized, and modern aesthetic that is both technically efficient and visually engaging. Defining the 2.5D style. In the context of a fighting game, 2.5D refers to gameplay that is constrained to a two-dimensional plane, while the characters and environments are rendered as 3D models with a perspective camera. This approach, popularized by games like Street Fighter IV and Guilty Gear, combines the strategic depth of classic 2D fighters with the visual fidelity and dynamic animation of 3D graphics. The camera may pan, zoom, or rotate for dramatic effect during special moves, but the core movement and combat remain on a single line of action. The meme theme implies an art direction that is not photorealistic, but instead leans into exaggerated, colorful, and perhaps even cel-shaded visuals, with flashy particle effects that emphasize the game's high-energy, arcade-like nature. The Character Asset Pipeline. Creating the playable characters from concept to in-engine asset involves a multi-stage pipeline that must be tightly integrated with the NFT minting process. Modeling and texturing. Characters are first sculpted and modeled as 3D meshes using software like Blender or Maya. Given the stylized theme, the models can have exaggerated proportions and bold silhouettes. Texturing is done in a tool like Substance Painter, focusing on clean, vibrant colors and potentially hand-painted or cel-shaded lighting effects to achieve the desired look. 31 on rigging and animation. A skeletal rig is created for each character model. This skeleton allows animators to pose and move the character. For animation, two primary approaches can be considered. Traditional 3D keyframing. Animators create key poses in 3D space, and the software interpolates the motion between them. This is the standard for most 3D games. 2D skeletal animation. Spine Dragon Bones. A highly efficient alternative for a 2.5D game is to use tools like Spine. In this workflow, the 3D model is rendered from a fixed angle into a series of 2D sprites, one for each body part. These sprites are then reassembled and animated using a 2D skeletal system. This technique can produce incredibly fluid, high frame rate animations that are very performant and have a unique, distinct visual style that would fit the meme aesthetic well. Engine integration. Unity. The final models, textures, and animations are imported into the Unity game engine. 31A. Character controller or rigid body component is set up to handle the physics and movement, constrained to the 2D plane. State machines are built to control the transitions between animations, e.g., from idle to walk to attack, based on player input. Particle systems and shaders are used to create the spectacular visual effects for special moves. Linking to the NFT. The final assembled character prefab in Unity is the digital object that is verifiably owned by the player via their Xrpl NFT. The metadata pipeline ensures that the NF token on the ledger points directly to the IPFS-hosted assets that are used to build this in-game character. When the game loads, it will check the player's connected Xrpl wallet for owned character NFTs, read the metadata to find the corresponding asset URIs, and load the correct character model for the player to use in the fight. Part 6. The Player Experience, a unified multi-chain interface. The technical sophistication of the dual-chain architecture must be completely hidden from the end user. The player's journey, from onboarding to claiming their winnings, should feel intuitive, secure, and seamless. This requires a thoughtfully designed user interface, UI, and a robust client-side wallet management system that abstracts away the underlying complexity.